So we're going to be talking about direct variation from Algebra 1 today, just as a quick refresher before we jump into Algebra 2's inverse variations and some things of that sort. So direct variation goes like this. You have y equals kx, right? Y is a variable, x is a variable, k is actually a constant. So you got your y variable, your x variable, and k, which is a constant. The k constant is called the constant of variation. All direct variations pass through the origin of a graph. So if I were to have a graph, every direct variation would start at this center point and it would head in some direction from that center point. It will always head down to the left or up to the right. I mean, there is both sides to your lines, but in general, direct variation is used concerning things that only have positive values. So you're really only concerned about from 0 to the positive side. But you could be concerned about other things at some point. All right? So we've got our direct variation. There's some real simple direct variations, such as those of you who babysit or have a simple part-time job where you get paid by family members, not get paid by anyone who has to pay state taxes. So if you get paid by a family member $10 an hour, you would have a direct variation equation for how much you make, y, is equal to $10 multiplied by how many hours you work, which would be x. Basic direct variation. Your slope is 10, your y-intercept is 0, and that's all it is. All right? However, you rarely are given something so simple. You are usually given something like this, a table. So let's make this table. So let's say I've got a table. And your table has a 2, a 3, and a 5. An 8, a 12, and a 20. This is your x, this is your y. I'm going to give you just a moment, and I want you to come up with a method to tell if this is a direct variation or not. So as was just asked, the way to tell is there a single constant number that multiplies by x in order to make y? So I have a shout-out answer of k equals 4. How did you get k equals 4 for this example? Where'd that come from? So just a basic noticing k equals 4 because you notice 2 times 4 is 8, 3 times 4 is 12, 5 times 4 is 20. And since it worked each time, that's how you got it. Well, there is a mathematical side to this. Instead of just looking at it and going, oh, I see the number, you could write 8 equals k times 2. Solve for k. What do you get? K equals 4. Then you could write 12 equals k times 3. What does k equal there? 4. And then you could write 20 equals k times 5. And what would k equal here? Once again, 4. So k equals 4 for all of these examples. So I would have y equals 4x is my direct variation. Finding that constant is important. Knowing that it makes an equation is more important. All right? Now I'm going to give you another example. And I want you to see if you can figure out a constant of variation for this one. So let's put this over here. Keep it working. Go ahead and try this example here. See if you can find the constant of variation for this example. This set is not a direct variation. In fact, I don't really know what variation it is, so I'm just going to write not a direct variation. And I'm not going to concern myself because I'm only worried right now about whether or not this is a direct variation. So that tomorrow and the days after we can start talking about inverse variations. Okay? I'm going to give you 3 examples. Your job. Figure out if it's a direct variation. If it is a direct variation, write the equation y equals kx, substitute in the correct value for k. If it is not a direct variation, write not a direct variation. So go ahead and pause here and try these three. Check if all three of them are direct variations. If they are a direct variation, write the final solution in y equals kx form. If they are not a direct variation, write not a direct variation.